Hello friends, let us utilize the theory discussed in previous lecture to construct a green function for some boundary value problem. So let us start with the problem here. First, before that, let us take a self-adjoint linear differential equation and try to see how we can construct a green function for this given linear differential equation. So here we have taken this, we will consider here the Green's function for second order differential equation of the form px y dash whole dash plus qx y equal to 0, where px is not equal to 0 on this entire interval ab, and px is a C1 function. C1 function means continuously differentiable function. First derivative is continuous on this interval ab with boundary condition ya equal to yb equal to 0, and we try to construct a green function for the given problem. Here it is to be noted here that this is a self adjoint differential equation. Here it means that the if we define this as operator Ly is equal to this px y double dash plus p dash x y dash plus q of x y, then its adjoint operator L star y is also coming out to be same. So here your L star is nothing but same L. So here we try to see the self adjoint linear operator for this. So now to begin with, let us take a solution y1x, and it is defined by the initial condition y1 a equal to 0 and y1 dash a equal to some non-zero constant alpha. Now it is to be noted here that if your coefficients are continuous function, then by the existence and uniqueness of initial value problem, we can make sure that such a solution exists. So we take one solution y1 which satisfy the first condition that y1 a equal to 0 and y1 dash a is not equal to 0. Now this solution need not necessarily satisfy the given boundary condition given at point B, that y1b may not be equal to 0. So let us assume that y1b is not equal to 0, but since y1x is a solution, so any constant multiple of y1x is going to be a solution of this problem. So it means that similarly that any constant multiple of y1x is again a solution of 1. Now again in the same way we can find out another solution y2x which is a 0 at the point B, but its derivative is non-zero at the point B. Now with the help of these y1 and y2, let us consider green function of this form. So here gxi is equal to c1 y1x when x is lying between a to xi, and c2 y2x when x is lying between xi to b. Now see, we have already seen that such a green function will satisfy certain condition. So first condition is that gxi is continuous at x equal to xi. So it means that at x equal to xi, the right hand limit and the left hand limit both are same. So it means that c1 y1 xi is equal to c2 y2 xi. Then we have a jump condition of its first derivative. So that c2 y2 dash xi minus c1 y1 dash xi equal to 1 upon p xi. Here we have assumed that gx xi is continuous at x equal to xi. This is a condition. Second thing, we have that gx xi has a jump of 1 upon p xi at x equal to xi, that is that gx here your x plus to x minus is equal to 1 upon p xi. So here if you look at here, then this will be what? Sorry, it is x minus to x plus. Okay. So if you differentiate here, then you will get c2 y2 dash xi minus C1 Y1 dash xi equal to 1 upon P of j. Okay. This you can write it like this. Okay. So this now it is given by this. So now we have two relation. One is C1 Y1 xi equal to C2 Y2 xi, and C2 Y2 dash xi minus C1 Y1 dash xi equal to 1 upon P xi. So now we can solve this, and since we already know that this Y1 and Y2 are linearly independent solution of the system, so this Wronskian is going to be 0. So Wronskian of Y1 and Y2 at x equal to xi is going to be non-zero. So with the help of this we can solve for our C1 and C2. So C1 and C2 can be you can find out the solution C1 and C2 as this: C1 equal to Y2 xi upon P xi plus P xi W xi, and C2 equal to Y1 xi P xi W xi. This you can get it here. If you look at here, what is this? C1 Y1 xi equal to C2 Y2 xi. So we can write it like this. This is nothing but Y1 xi Y2 xi, and here we have Y1 dash xi minus, and here we have Y2 dash xi, and C1 and C2 is equal to, so here we have 0 and here we have 1 upon P xi. So this is an algebraic equation. This we can solve, and you can get the value of C1 C2 using Cramer's rule. So Cramer's rule says that this is 0 1 upon P xi, determinant of this, and Y2 xi and Y2 dash xi, determinant of this, divided by determinant of this. Determinant of this is going to be Y1 Y2 dash minus Y2 Y1 dash. So these, I think there is a small mistake here. This is minus Y2, so this is a minus thing. So here it is minus thing. Okay, and here we have now it is okay. So this is nothing but this, you can get it as Y2 xi upon Wronskian of Y1 and Y2 at xi. By Cramer's rule we can find out the value of C1 and C2 as follows: C1 equal to Y2 xi upon P xi W xi, C2 equal to Y1 xi divided by P xi W xi, and we can get our Green's function defined as this. So here we have done this thing, and if you remember, we have assumed that our Wronskian is non-zero. So it means that we have assumed that Y1 and Y2 are two linearly independent solution. So how we followed? If you remember, we have written what is Y1. So here we have assumed that Y1 and Y2 are two solutions of say Ly, which is defined as Px y dash whole dash plus Qx y 0. So this is a linear differential equation. We have assumed that Y1 Y2 are two solution here, such that Y1 a equal to 0 and Y1 dash a is not equal to 0, Y2 p equal to 0, and Y2 dash b is not equal to 0. And also we have assumed one more condition on Y1, that Y1 b is also not equal to 0. So with the condition that Y2b is equal to 0 and Y1b is not equal to 0, and Y1 Y2 both are the solution of Ly equal to 0, here we have this is possible only when Y1 and Y2 are two linearly independent solution. So that's why we are able to write down the solution as this, because if your W xi is going to be 0, then we cannot write it like this. So now let us discuss here. and so node 1 is precisely the same thing, that the solution y1 y2 are of the equation 1 that we have chosen are linearly independent by the virtue that y1b is not equal to 0, but y2b is equal to 0. Now it may happen that for a given second order equation of the form, because what we have discussed is the particular case when we have a self adjoint, that linear differential equation is given in self adjoint form plus boundary conditions are given in a homogeneous form. Now it may happen that in general it may not be true. It means that your equation may not be a self adjoint equation. So it means that y double dash plus p1x y dash x plus p2x yx is equal to 0. So here the condition that the coefficient of y dash x is not the derivative of coefficient of y double dash x. So this is not given in terms of homogeneous form, this is not given in terms of self adjoint form. And if you look at the condition also, here condition is given as ya equal to a and yb equal to b, and A and capital B may not be equal to 0 ideally. So what to do in this particular case? So the first thing, that this equation can be converted into self adjoint form by multiplying by this integrating factor. I can tell you just if you look at here, y double dash x plus p1x y double dash x plus p2x y, this is y dash x, y equal to 0. Now what we try to do is we just multiply by some say function, let us say px is integrating factor. So px y double dash x plus px p1x y dash x plus px p2x y equal to 0, and we have already discussed that this is in self adjoint form if coefficient of say y dash x, that is px p1x is equal to derivative of the coefficient of y double dash x. So it means that derivative means p dash x. So if you look at this is a simple differential equation in terms of p of x, px is unknown, p1x is already given to you because equation is given, so p1x is given to you. So this you can solve as p dash x divided by p of x is equal to p1x. So it means that this you can find out. So px is equal to, you can take e to power integration of p1x dx. So by multiplying, so it means that any equation which is not given in self adjoint form, you can always make them self adjoint form by multiplying this factor px, which is e to power integration of p1x dx. So you multiply by this factor and this can be converted into self adjoint form. Now second thing, that the condition 9 means this thing, y of a equal to a and yb equal to b, we want to make it 0 condition. So for that we take a linear transformation from which take the point this capital A capital B to 0 0. So what we do here, we simply take transform zx equal to yx plus this quantity. In fact it is this, you take z of x is equal to y of x plus alpha x plus beta. Now we choose alpha and beta in a way such that this condition is transformed to homogeneous condition. If you look at condition are what, y of a equal to capital A and y of b is equal to capital B. So what we want here, that z of a is equal to 0 and z of b equal to 0, right. So this is basically what, this is your 0 equal to y of a small a is basically capital A. So this is your capital of A plus alpha A plus beta, and here it is what, it is 0 and at point B. So it is at x equal to A and at x equal to B it is what, z of b is 0 that we want and y of b is capital B plus alpha b plus beta. So with the help of this you can easily find out what is your alpha and beta. Is that okay? So using this linear transformation you can convert our non-homogeneous condition to a homogeneous condition. So now if we do this, then we are using a new variable zx. So your equation will also change. So initially your equation is your Ly equal to 0, but when you use z of x equal to yx plus alpha x plus beta, then it will be reduced to something kind L tilde z equal to your sum f of x here. Now here, by since L is a linear operator, so L tilde is same as L here. So this will be reduced to L of z equal to f of x. So what is f of x? F of x can be given in this particular form. So f of x is given by this expression, that minus of a plus b minus a, capital B minus a divided by small b minus a, x minus small a, qx minus capital B minus a upon b minus a p of x. So with these two things, any second order linear ordinary differential equation can be converted into a self adjoint form with homogeneous boundary conditions. So it means once we have converted form, then this procedure will give you the method to construct green function for this. So with the help of this, we can construct green function for any second order linear differential equation with any type of condition, whether it is homogeneous boundary condition or non-homogeneous boundary condition. You can always find out your green function. Okay. Now let us use this and the previous theory which we have discussed to find out some green function. So first example, let us consider here that y4x is equal to 0 with the boundary condition given in this particular form. If you look at here, this problem is also given in terms of self adjoint form. So here L is your fourth derivative of y with respect to x. So its adjoint is same as this. Okay. So now let us consider the construction of green function. So here the general solution is given by this. So yx is equal to let me write it here. So equation is what? L is basically Ly is given as fourth derivative of x. So here your general solution, you can find out y of x is given as a plus bx plus cx square plus d of x cube. So your first condition that if you look at your theorem, the first condition here that this boundary value problem has a trivial solution. So just verify that thing. So if you use the boundary condition is y0 y dash 0 equal to 0, y1 equal to y dash 1 equal to 0. So if I use this condition, y of 0 equal to y dash 0 equal to 0 and y of 1 equal to y dash 1 equal to 0. If you use this, you can see that all these conditions a equal to b equal to c equal to d all are 0. So it means that this homogeneous boundary value problem will have a 0 solution. So here we can construct a green function to solve this particular problem. So now let us start with the construction of green function. So green function is again, as we know that first condition on green function is that it is the solution of operator L here, right. Since it is self adjoint operator, so we can write it that G is the solution of this L of G is equal to 0 for x not equal to xi. So let us take that gxi is equal to a1 plus a2 a1 plus a2x plus a3x square plus a4x cube, and x is lying between 0 to xi. Similarly we can define for xi x lying between xi and 1. So and here we need to find out all these coefficient a1 a2 a3 a4 and b1 b2 b3 b4 such that it satisfies the certain condition. If you look at the condition on this, that G is continuous, not only G, n minus 2th derivative of G is going to be continuous here. So n in this case it is 4. So it means that G and G dash and G double dash is continuous. Let me write it in a proper form, that Gxx is continuous at x equal to z, and G triple x and xi minus to xi plus is equal to 1 upon the coefficient here is p naught is 1 here, so it is 1 here. So we will have this thing. So condition is given by this. If you use this condition and the fact that I am just assuming that Ci is equal to Bi minus A of I, then we can write down these conditions in this particular format. I can write it here, that C1 plus C2 xi plus C3 xi square plus C4 xi cube equal to 0. Here we are using that Gxi is continuous at x equal to xi. Second is C2 plus C3 2 xi plus C3 times 3 xi square equal to 0. Here I am assuming that G dash x is continuous at x equal to xi. Similarly, here I am using that Gxx is continuous as x equal to xi, and this last condition is showing the jump condition, that third derivative of G with respect to x is having jump of quantity 1. So C4x equal to 1. So with so we have 4 conditions and we have 4 unknown, so we can find out C1, C2, C3, C4. If you solve this is a simply triangular system, so you can easily find out C1, C2, C3, C4. So now how to fix how to find out A1, B1. So now utilize the boundary condition. So boundary condition is that at point 0 G0 xi is equal to 0 and Gx 0 xi is equal to 0, G1 xi equal to 0, Gx 1 xi is equal to 0. If you use this condition, you will get equation condition on A1, A2, B1, B2, A1, A2, A3, A4 and B1, B2, B3, B4. So we have condition A1 equal to 0, A2 equal to 0, B1 plus B2 plus B3, B4 equal to 0 and B2 plus 2B3 plus 3B4 equal to 0. So using these 4 conditions and the value of C1, C2, C3, C4, you can easily find out all these conditions A1, B1, A2, B2, B3, B4, and with the help of B3, B4 you have A3, A4. So now we are able to find out all these AIs and BIs for this, and with the help of this now we can write down our green function in this particular form, Gxi equal to this in interval x less than equal to xi, and this equal to when x is greater than equal to xi. And here we can note this, that Gxi is same as G of xi x. So it means that this green function is a symmetric green function, and this is quite clear because we have assumed we have taken this operator y fourth derivative of x d4 by dx4, and it is a self adjoint operator. So green function is going to be a symmetric green function. Okay, now let us consider another example. If you remember, we have assumed one condition that the coefficient of the highest order derivative is non-zero in the entire interval a and b, but suppose it is not. Suppose your coefficient of the highest order derivative is 0 at one of the endpoint. For example, if you look at here, xy double dash plus y dash equal to 0. So this is a ordinary differential equation. So if we take interval from 0 to 1, right, so if we take this interval from 0 to 1, then the coefficient of y double dash, which is x, is going to be vanished at point x equal to 0. So it means that here we have to define our boundary condition in a way such that we can construct our green function. So here we have put another condition, that is yx is going to be a bounded function as x tending to 0. So this is a natural condition which is coming through coming from the equation itself. So if there is any coefficient of highest order derivative is vanishing at one of the endpoint, then we will assume that your solution is going to be bounded at that particular endpoint. And the other boundary condition is given here, that y of 1 equal to alpha y dash 1. Here alpha is some non-zero constant. So here first of all, to construct our Green function which is a solution of L of G equal to 0, if Ly is defined as x y double dash plus y dash equal to 0. So first of all, we try to find out the solution of this particular differential equation. So here we have just assumed that y dash x equal to z of x, and then we can then this can be transformed into this xz dash plus z equal to 0. So here we have taken this. So here we have x y double dash x plus y dash x is equal to 0. So what we try to do here, we take y dash x equal to z of x, or you can simply say that it is a Cauchy-Euler equation in terms of y dash x. So here if we assume this, then it is what, x z dash x plus z of x is equal to 0. So you can find out what is z of x, and then once we have z of x, then you can find out y dash x as this condition z dash x. Once we have z of x, you can find out y of x. So if you solve this, your solution is going to be, so here your you can solve it here, z dash upon z equal to so minus 1 upon x. So here we can say that ln z equal to minus ln of x plus ln of c here. So z is equal to c by x here. So using this, you can find out yx here. So y of x is equal to c of x here. So y dash x equal to c by x. So yx is going to be c of ln of x. So here we simply say that x is greater than 0. So here put this is just to define it. Okay. So our solution is going to be y of x is equal to c of ln of x plus, if you look at one obvious solution of this particular problem is any constant solution. So you can write it here, c1 ln x plus c2. So it means that the general solution of this equation is written as yx equal to c1 ln x plus c2. Now if we assume the condition, boundary condition, which is given as yx is bounded as x tending to 0, then this c1 ln x plus c2 will remain bounded as x tending to 0, provided that this c1 has to be 0. So it means that first condition, that your solution is bounded at x equal to 0, force us to assume that c1 is equal to 0. And then if you look at the other boundary condition, that is, so c1 is equal to 0 because yx is bounded at x say at x tending to 0, bounded as x tending to 0. So c1 is equal to 0. Now if you look at the other boundary condition, that is y of 1 is equal to alpha y dash of 1, then you can say that y of x equal to c2, then y of 1 is equal to c2, but y dash 1 is going to be 0 here. So this implies that your c2 has to be 0. So c2 has to be 0. So it means that this homogeneous boundary value problem has only trivial solution. So now once we have this condition, then we can only construct our Green function. So here a Green function is now constructed as gxi as linear combination of your solutions and between x to xi, and b1 plus b2 ln x between xi to 1. Okay. So here this a1 a2 we can find out that it will satisfy the boundary condition given at the point A, and b1 plus b2 ln x is the we can find out using the condition that this is going to be this is going to satisfy the boundary condition given at the point 1, right. So now from the continuity of gxi, we have b1 plus b2 ln xi is equal to a1 plus a2 ln xi. So we have this condition. Now jump condition, if you look at, then the derivative of this, so that is b2 by xi minus a2 by xi is going to be 1 over xi here. Yeah, here P naught xi is nothing but xi here. So now using Bi minus Ai as Ci, I can write it C1 equal to B1 minus A1 and C2 equal to B2 minus A2. So if you use this notation, then this condition is going to be reduced to C1 plus C2 ln xi equal to 0, and here it is C2 by xi equal to 1 by xi. So C2 is coming out to be 1 and C1 is minus ln of xi. So using this, now we put that condition that this A1 plus A2 ln x satisfy the boundary condition given at the point x equal to 0, and B1 plus B2 ln x satisfy the condition satisfy the boundary condition given at the and 1. So if you use this, the boundary condition given at the point x equal to 0 is that your solution is remains bounded at x equal as x tending to 0. So that simply shows that A2 is equal to 0, and this condition that gxi equal to alpha gx dash xi implies that B1 equal to alpha B2. So if we use this and C1 C2, you can easily write down that your gxi is equal to alpha plus ln xi for x less than or equal to xi, and equal to alpha plus ln x as xi less than or equal to x. So you can construct our green function like this. Now let us consider one more problem. If you remember, the first problem we have discussed is the fourth order derivative, fourth order linear differential equation. Second problem we have considered where your coefficient of highest order derivative is vanishing. Now let us consider one more condition, one more example, so that we have a better understanding of construction of green function. So here this is the famous problem, y double dash x plus k square y equal to 0, y0 equal to y1 equal to 0. So if you look at, we can find out the solution, and the solution is given by sine of k of x. Now if we use a boundary condition that y of 0 equal to y1 equal to 0, then we have that the solution given is 0. Let me show it here. So this is your y double dash x plus k square yx equal to 0. Here y of 0 equal to y of 1 equal to 0. So if you solve this, the general solution of this is given as y of x equal to c1 sine of k of x plus c2 cos of k of x. And if you use the condition that y of 0 is equal to 0, this implies that c1 it is 0 here plus c2. So this implies that c2 is equal to 0. Then y of 1 equal to 0 means c1 sine of k equal to 0. So if k is not your n of pi, here k is some given number, then you can say that this simply implies that c1 equal to 0. So it means that your y of x is nothing but a trivial solution. So now we can proceed for finding green function for this particular problem. So to start with, let us take one solution. Say we already know that y of x is equal to c1 sine of kx is a solution which satisfy the condition y of 0 is equal to 0. So let us take y1x as this sine of kx, we satisfy the boundary condition given at the point x equal to 0. Now take the another solution y2x, we satisfy the boundary condition given at the end, that is x equal to 1. So I can take this sine of k x minus 1. You can take any linear combination of sine kx and cos of kx, and ultimately you will get the same thing. Okay. So here you may start with you may choose your y2x as some alpha times sine of k of x plus cos of k of x, right. So such that y2 of 1 is equal to 0. So if you put y2 1 equal to 0, you will get what? So this is 0 equal to alpha, your sine of k plus beta here, beta cos of k here. So, you can get your alpha and beta, you can write it beta is equal to minus alpha sin k upon cos of k. I am assuming that cos of k is non-zero. So, y2 of x is equal to, I am writing here alpha sin of kx plus beta I am writing here as minus alpha sin of k cos of k and cos of k of x. If you simplify, what you will get, if you simplify alpha times, here it is what, sin of k of x cos of k minus sin of k cos of kx, or this you can write it that alpha of sin of k x minus 1. So, that is what I am using. You may start with this, or you can directly write it this y2x sin as sin k x minus 1, it is both way correct, you can use anything. So, here we assume y1x equal to sin kx, we satisfy the boundary condition at x equal to 0, and y2x equal to sin k x minus 1 as satisfy the condition y2 1 equal to 0. So, with the help of this let us find out say Wronskian of this. So, Wronskian of this y1 and y2 is coming out to be k sin of k, you can easily calculate of this, you can easily calculate this, and then with the help of this you can write down gxi as this. Is that okay? So, this is all for today's lecture. In next class we will discuss the use of green function for forming of integral equation and solving the boundary value problem. Thank you for this.